Namaste to everyone. Welcome to my YouTube channel. Today I will deliver my lecture on tensor analysis, lecture 8, which includes miscellaneous problems on the lecture delivered from 1 to 7. Before starting the miscellaneous problems, I would say something that some persons may confuse on using alpha as a dummy suffix always, but no one has to be confused as I am giving the idea. AIXI is a term in which I stands for a dummy suffix. This means A1 x1 plus A2 x2 plus dot an xn. In place of I, we may write also alpha, a alpha x alpha. Here alpha is a dummy suffix, so we may write values of alpha 1, 2 and so on. Alpha equal to 1, a1 x1, alpha equal to 2, a2 x2 plus alpha equal to n xn. So in place of I, we may write alpha or any index that will be treated as dummy suffix. Also in contravariant tensor, contravariant vector, we have already seen that a bar I equal to del x bar I del x alpha a alpha. We have used here alpha as dummy suffix. So in place of alpha, we may also write any index, that is a bar I equal to del x bar I by del x L al. We may write any index which will be a repeated suffix. Now problem 1. If Aij be a covariant symmetric tensor and this is covariant and this is contravariant, Aij contravariant tensor, be a to the power minus 1 times the cofactor of Aij in the determinant, this Aij n by n equal to 1, then so that number 1 Aij means contravariant determinant equal to determinant n by n equal to 1 by n. And second problem is Aij covariant, Aij contravariant equal to n. From the definition of conjugate tensor, we have Aij equal to means 1 by a into cofactor of Aij, that was Aij. So this tensor, this contravariant tensor is a conjugate of this covariant tensor Aij. Now we shall prove number 1 as Aij equal to 1 by a multiplied by capital Aij. That is the cofactor of small aij. Take a determinant in both sides. Aij determinant n by n, determinant 1 by a Aij n by n. If we want to take out 1 by a, it will come out as 1 by a to the power n into determinant of Aij. This is determinant of cofactors. So this will be 1 by a to the power n value of this is a to the power n minus 1. We will verify this. This equal to 1 by a, proved. But we will verify the value of this determinant equal to a to the power n minus 1. We know that a adjoint a equal to determinant a in. Taking both sides determinant, a adjoint a equal to determinant, this is n by n, determinant a in, this is also determinant. Inside this is a matrix whose diagonal element are determinant a. So if we take out, we will get a to the power n determinant in. Determinant of in equal to 1. So this is determinant of this n by n. Each determinant is n by n. Left side now. Left side is the product of matrix A and adjoint A, and this is the determinant. So it will give determinant A n by n, adjoint A n by n equal to determinant A n by n. Determinant a to the power n by n implies that adjoint A determinant equal to, this is value of this is a, determinant of a is a to the power n, and this is also a, this is a, this is a to the power n minus 1. Adjoint A contains the cofactors of the original matrix as an elements, and adjoint A is a matrix which is transpose of a matrix whose elements are cofactors of the original matrix. And we know also that the determinant A and transpose of A, that is determinant of A dash, both are equal. So this will be Aij equal to a to the power n minus 1. So we have verified the result that determinant of the cofactors is a to the power n minus 1. Now we solve the next one, Aij into contravariant Aij equal to n. We know that Aij Ajk equal to Aij Akj, as conjugate tensor is symmetric. This equal to Aij, and conjugate value of conjugate tensor is Akj by value of the determinant. This will be Aij Akj into 1 by a. This equal to 1 by a. Here j is the dummy suffix. Ai1 capital A K1 plus Ai2 capital A K2 and so on. Ain Akn. This is the element and this is the cofactor. This is the element cofactor. If sum of products of elements and corresponding cofactors will give the value of the determinant. So we may write this as determinant A Kronecker delta I k equal to delta I k. Putting k equal to I, we get Aij Aji equal to delta II. This will be delta 1 plus delta 2 plus delta Nn. This side, this is symmetric, so we may write Aij equal to, value of this is 1 plus 1 plus 1, n numbers of 1. This is n. So second number is put. Our second problem is if Aij covariant tensor equal to 0 and when I not equal to j and Aij not equal to 0, I equal to j. That means this is Aij I not equal to j means non-diagonal elements are 0, and this is I equal to j means diagonal elements are not 0. Then the conjugate tensor Aij equal to 0 for I not equal to j, and conjugate tensor Aij equal to 1 by covariant tensor Aij when I equal to j. Let us write all elements in matrix form: A11, A12, A1n, A21, A22, A2n, An1, An2, Ann. As non-diagonal elements are 0, here we write non-diagonal elements are all 0, but diagonal elements are non-zero. If we take the determinant of this matrix, whose value is small a, then it will be the product of diagonal elements, means A11 into A22, Ann. Now cofactor of A11 is A22 multiplied by A33 multiplied by Ann. Now conjugate tensor A11 is this is cofactor of this A11 by determinant. Value of this is A22, A23, A33, Ann by determinant. Value of the determinant is A11, A22, Ann. So we get 1 by covariant tensor A11. Similarly, we may find the value of A22. A22 will be here A22. Here A22 will be A11, A33, Ann. So here we write A11. So we will get A2. Similarly, all diagonal components of conjugate tensor will be Ann equal to 1 by Ann. N may be 1, 2, 3, n. Non-diagonal components. If we take A12, value of the cofactor of small a12, this will be 0. So a12 equal to a12 by determinant A, means 0 by A equal to 0. Similarly, other non-diagonal conjugate tensors will be 0, hence proved. Next problem is, if f is a scalar valued function of coordinates xi is the coordinate in x system of coordinates, then show that del f by del xi is a covariant vector, or the gradient of scalar function is a covariant vector field. This f is a function of xi, means x1, x2, xn. xi is a coordinate in x system of coordinates. In x bar system of coordinates, the coordinates are x bar 1, x bar 2, x bar n. So, x system of coordinates be the function of x bar 1, x bar 2, x bar n. If we differentiate this, del f by del x bar I. This is bar system of coordinates. So we may not differentiate directly this. So firstly we have to differentiate f with respect to the coordinates of x systems. Then we will differentiate with respect to x bar system. So we may write del f by del x1 first. Del x1 by del x bar plus del f by del x2, then del x2 by del x bar I, and so on, plus del f by del xn by del x bar I. Here we see that 1, 1, 2, 2, nn. So we may write this in the form of dummy suffix. This will be del f by del x alpha by del x bar I. Rearranging del x alpha by del x bar I, del f by del x alpha. So this partial derivative represents that del f by del x alpha or del f by del x bar I are components of covariant vector. Thank you for watching my video. I will continue the miscellaneous problem, which are the remaining problems, in my next lecture. If you are satisfied with my presentation and contents, please click on like button and do subscribe my channel.